Section 3.2 is addition and subtraction of whole numbers. So for those of you who are wanting to work with the littlest ones, right? The pre-K, the kindergarten, maybe the first grade area or whatever, you're probably going to really like some of the stuff in this section. One of the things that I want you to remember is that math is different. Math is not different. But the ways in which we have to explain and show math is different than when you were 6 years old. Okay? So right now, I want you to put out of your mind the fact that you already know how to do everything I'm going to show you, because I'm going to show you some things you probably haven't seen before. And some of the things you'll use, some of the things you probably won't. It'll depend on what curriculum your school districts are using and things like that. My goal is to make sure that when you get to that environment, you're not looking at things that you're like, I wish somebody had told me what in the world I was seeing. I've never seen this before in my life. So our role in this class is to make sure that we can introduce you to as much as possible of what you might see if you entered this environment today, okay? So that's what we're going to look at. All right, so to start with, addition and subtraction, the definition of addition. If A and B are two disjoint finite sets where the cardinal number n of A is A and the cardinal number of B, n of B is B, then A plus B equals the number of items in their union, A union B. The lowercase a and b are called add-ins, and A plus B is called the sum. In reflecting upon my own early childhood experiences, I don't feel like that the vocabulary was used as extensively in the classroom as it is today. I hear the words add-ins and sum used a lot more when I've seen my own children bring home papers and things like that. So you're probably going to see more of it than you remember experiencing. Now within this definition, it talked about A and B being disjoint. So the first thing we're going to do is we're going to talk about why A and B have to be disjoint for this to happen. Now take a look at what else they defined A and B to be. It said they're disjoint, but it also said they were finite. What did finite mean? Sorry, there's so much loud noise, you're going to have to like yell at me today. What did finite mean? Okay, there's an end to it. It stops somewhere, right? Sometimes we also think about somehow we could maybe like list them all out or something like that, right? There's no ... needed kind of a deal. So when we create this, we need to make sure we're creating finite sets. So let me talk about A first, and we will define A to just be a few numbers. And we're going to go 1, 2, 3, and 4. That's finite, right? There are 4 items in this set. So one could actually say that n of A, remember that means the number of items in A, is equal to 4, because there's 4 of them there. Set B. Now what we're wanting to create when we create set B is something that's finite, but it's not disjoint. So what does disjoint mean? If these were disjoint, what would be the property that they have? Anybody remember? They don't have anything in common, exactly. So disjoint means they don't have anything in common. So if we're trying to say, well, what would happen if they did, we're going to create something that has something of this in common. So I'm going to use 3 and 4 for a couple of things they have in common, and then we'll do 5, 6, 7. Again, there's nothing special about this example. The only condition really that they have to do in order to make this example work is be not disjoint. They have to have something in common. So if I count this, one is n of b. It's 5, exactly. N of a is 4, n of b is 5. And what it said over here is that there's going to be a way of adding a and b together that's the same as counting the items in the union. So we've just done a whole lot of work on unions and intersections. What would the union of A and B equal in this environment? 1. What else? 2. 3. Okay, so it's just the collection of everything. Union means you get it all. So count for me. What are the number of items in this union? 7. And is that equal to 4 plus 5? No, these are not equal. So what's the deal? Why is it that we need them to be disjoint?
The numbers that are the same aren't going to be counted twice.
Yeah, there's double counting involved, right? If we have things that are not disjoint, like A and B weren't here, things will get counted twice. They will get double counted. So we gave the example and so forth, but just as a written work of what we did is we're going to write the statement down to justify to ourselves if A and B are not disjoint, what they have in common will be counted twice. And that's what happened when I counted and I got 5 and 4 up here. The numbers, the elements 3 and 4 got counted twice. All right, we're going to look at 3 models for addition. 3 models for addition. The first is called a set model. So a set model is used for whole objects. And I've got an example to describe a set model. Liz has 3 blue crayons and 2 red crayons. If she combines all the crayons, how many crayons does she have? So this is the model. I mean, that's it. A model is a word problem that fits a specific criterion. This is the set model word problem. And what I want to show you next is a concrete way to solve this problem. Okay, for the littlest of children, this would be an example. So we're going to create, if you have colors with you today, you might want to have them out. It's not a requirement, but you certainly could. So we're going to use, I wanted to start with red crayons, 2 blue crayons. So here's crayon number 1, crayon number 2. I got 2 blue crayons. Oh, sorry, thank you. 3 blue crayons. It was 2 red? All right. And then I have 2 red crayons. And so my total, of course, if I were to count then, is 5 crayons. So this is a set model. Set models are really nice because we don't have to worry about how big the crayons are, right? I mean, a crayon's a crayon. It doesn't matter if it's the long twisty crayons or if it's the short crayon or if it's the sort of half-looking kind of crayon that nobody ever wants to use anymore and it's in the dirty crayon bucket. Y'all know what I'm talking about, right? They all count as one, right? I mean, that's how we sort of think about this particular object. So they work really nicely to talk about with a set model. The next model we're going to look at is called a number line or measurement model. This is typically used for objects that can be partitioned. Now, we're still using whole numbers. There's no decimals or fractions in what we're doing in this chapter, okay? We're still using whole numbers. But the objects that we're describing are things that would make sense to have half of, or something like that. For example, Joe has 4 feet of wood and 3 feet of aluminum. Well, he could have half of a foot of wood and it would make sense. So that's what it means to say that it can be partitioned. And the question is, how many feet of building material does Joe have? Now, I guess you could actually draw it out like this. I mean, you could, but that's not really what's visually going on, right? Visually, the pieces of wood and the pieces of aluminum are all just contiguous, right? They're in a row. They're not already disconnected like my crayons were. So my image looks a little bit different when I'm solving it, and a number line model is a really nice way to solve it. So draw yourself a number line. You're welcome to make it start at 0 if you'd like. And what we're basically going to do is we're going to lay our pieces of wood or whatever along our number line. So I'm just going to mark them off so I can make sure that I have my width and length that are right here. Okay, so this is just for the purposes of drawing it sort of to scale. It says he has 4 feet of wood. So if you imagine laying his pieces of wood out here, like, that's really too thick. Let me try and make it a little bit thinner. My piece of wood. This is 4 feet of wood. And then I have 3 feet of aluminum, end to end, if I draw it nice enough. And of course the question is, where do I end? And you could fill all the dots in, right? This is 1, 2, 3, so there's my 4, and then I have 5 and 6, and I end at 7. So this is 7 feet of building material. I hope you notice that as I do the problems, over here it wasn't the answer 5, the answer was 5 crayons. And here the answer is not 7, the answer is 7 feet. So if we've got context in the problem, then the answer should have context as well, okay? All right, there's some more models we're going to do for subtraction later on, but kind of in between these, we're going to talk about a couple other things. First one we're going to talk about is the phrase less than. For any whole numbers a and b, a is less than b, and it has that symbol, if and only if there exists a natural number k, such that a plus k is equal to b. Now, before I ever wrote it out like this, you innately know that this is true, right? The reason that 4 is less than 6 is because there is some number that I can add to 4 to make it equal to 6. That's why this is true. And that's what this definition says, is that there is something that I can sort of fill in the blank here with to make it true. If there isn't, then it's not less than, right? The reason, in some sense, that 6 is not less than 4 is because there is not a whole number I can fill in this blank right here and equal 4. There's not a whole number that does that. So that's why that 6 is not less than 4. Now, just because I defined it with addition doesn't mean that it had to have been defined that way. We could define less than using the idea of subtraction as well. So I want to give you an example of this because in your book you're going to do the similar thing with your homework where you're going to define a greater than, something about being greater than in terms of addition or subtraction. So what is written over here is almost identical to what I'm going to write about subtraction. The part that's going to be different is this part at the end because this has addition in it, and the other one that I'm going to do is going to have subtraction involved. So if I'm modeling this, it'll start out the same, and it'll say for any whole numbers a and b, a is less than b. Written. A is less than b. If and only if there exists a natural number k, such that, so far I have written word for word what was on my other problem, right? I mean, it's word for word. What would the last piece be, though? Because it's different. What would this need to say to make this work with subtraction? The goal is to make it with subtraction.
B minus K equals
Yeah, I'm going to rewrite it the other direction from what you just said, but yeah, A is equal to B minus K. Or if you want to write it the way that Zion said, B minus K is equal to A. Okay, that's this. I made this look like I've got fraction, and it's not a fraction. Okay? Either of these can go right here. Okay? Whichever one you like better. But that makes sense, right? The idea, the reason again that 4 is less than 6 is because there is a number that I can take away from 6 to get back to before. That's what this definition is saying, as opposed to there's a number to add to the 4 to get me up to 6. Today we're going to start our discussion of properties. We have 4 whole number properties for addition. And as we expand into subtraction, multiplication, and then eventually integers later on in chapter 5, we are going to keep coming back to these definitions over and over and over again of these properties. So our first property is the one that trips people up the most. It's called the closure property. The closure property says if A and B are whole numbers, then A plus B is a whole number. Okay, so imagine if you take any 2 whole numbers, remember whole numbers are 0, 1, 2, 3, and up, and you add them together, do you get another whole number? Yeah, you do. Now that doesn't work with all numbers in general. So let's say, for instance, that we weren't talking about the whole numbers, we were talking about odd numbers. What happens when you add 2 odd numbers together? Do you get another odd number? No. Yes. Answer. What do you get? Do you get an odd number when you add 2 odds together? You don't on that one, right? You don't get another odd number. So the fact that this is working for us is working very specifically because it's whole numbers and it's addition. We'll talk next class period what happens with subtraction. This doesn't work for subtraction either for whole numbers. So if I keep my whole numbers but I do subtraction, what happens when I do 3 minus 5? Not a whole number, right? Okay, so here's one visual description of how you can think about whole numbers. This one I like a lot. Imagine whichever number system you're working in. We're working for whole numbers, but let's think about it for a moment with odds. Okay, just imagine you have odd numbers only. We're in a room, it's got a door closed. I know we got some windows open, but pretend we don't. Okay, so we're in a closed-in environment and all the odd numbers are floating around in the room. Okay? The set is closed if when I take the 2 odd numbers and I add them together, I get another number that's in the room. That is to say, I don't need to open the door to find the answer. It's closed. Now, odd numbers don't work, right? 2 odd numbers added together don't give me an odd with addition. But do odd numbers work with multiplication? They do. All right? So you can vary, more than one thing. You can vary the operation you're working with. I gave you some examples already with different things that happen with subtraction and multiplication. And you can also vary the type of set that you're working with to talk about closure. And you've got some examples with varying the types of sets that you're using in your homework and stuff for this section. They ask questions instead of odd. They talk about what happens if you have, multiples of 3. What's going to happen with multiples of 3? And they ask the same kinds of questions, okay? Commutative is the next one. You probably remember commutative. Commutative property says that if you have A and B as whole numbers, then A plus B is the same as B plus A. We've been working with this with our son with his multiplication facts recently. That as he continues up the multiplication track, right? So he's done his 1s and his 2s and his 3s and his 4s, and he's all the way up to 12s now, so he's actually done. But when he was about in the 7s and 8s, my husband kept telling him, you know half the numbers already. You already know half of them, right? Because when you get to 7 times 8, well, you already did it when you did 8 times 7, or vice versa. You already know half of the answers that you've done. So that's what's going on with commutative, and we use this extensively for children. Sometimes it's easier for them to start with the bigger number than the smaller number and think about the addition, right? So there's the commutative property. The next one is the associative property. The associative property says that when I have 3 numbers, A, B, and C, I should say if A, B, and C are whole numbers, my bad. That A plus B plus C, where the A and the B are added first, is the same thing as if we'd added the B and the C first and then added the A. And sometimes that's very helpful. And the reason it might be very helpful is because two of the numbers add up to like 10. That's nice, right? If I have 8 plus 3 plus 2, well, it'd be easier to add 8 plus 2 and then add the plus 3 because they make to something nicer to work with. And then the last property is the identity property. The identity property says that there's a unique whole number, and it's 0. 0 is called the additive identity. So if I talk about the additive identity, I'm talking about the number 0. If I talk about the identity property, I'm talking about the fact that this 0 thing exists. Such that for any whole number, A plus 0 is equal to 0 plus A is equal to A. Okay? So what we're going to finish up with real quick is identifying which property we have presented to us on each of these 4 problems. And then we're going to get into groups, and we're going to do group work from section 3.1. So what property do you see listed on number A, letter A? That is the commutative property. Please spell that right. I know that sounds like an obvious statement, but every time I give tests and things on this, I get somebody telling me that it's the commutative property. The communicative property. There are some of these words that mean something different. Commutative. Okay, how about B? What property do you think is happening on B? It's not associative. That's a good guess. It's identity on this one. So I've got that plus 0 on one side, and it's not affecting the other side, right? So this is the identity property, but we need to make sure that we say the additive identity, because very soon we're going to have a multiplicative identity, and it's not the same property. So this is the additive identity property. How about C? It is commutative. So Taryn, tell me what you see commuting.
Because like it wouldn't be associative because they're just switched within the parentheses.
Okay, so even though it sort of looks like I've got 3 numbers, well, it doesn't just sort of look like, I do have 3 numbers added together. The parentheses values that are inside the parentheses don't change. It's the 8 and the 6 that are still inside. It's just the order of the 8 and the 6 that switched. So this is simply another example of the commutative property. And how about D? That's the associative property. Best not to abbreviate that. And the reason is because you see the 5 and the 3 here, and then here you see the 5 out in front with the 3 and the 2 inside the parentheses in that one.